Okay, so although PD3 is not finished yet, but I still would like to do a smallish demo on PD4 because PD3 is due on Sunday, and hopefully you'll start on PD4 after that. So you won't have a lot of time after that to finish PD4. So better to do the demo now, and maybe when again we have a class, we can have another small demo if you need more information on how to do this. Okay. So I'll show you some of the extra things I did for PD4. So this is mostly the code of PD3. Like this is the code I showed you and uploaded to Backpack for PD3. However, there are some small additions for PD4. So the first addition is, for example, this one. So let's see here. So the first addition is this one, that every symbol now not only has a name and a type, but it also has an offset. Okay, so it's basically what is suppose it's a local variable. What is the offset from the top of the stack at which the local variable resides? That's what this offset says. Okay, any questions about this? So when I am like creating a new symbol, like I'm sending this additional argument called offset just to set it. Okay. So same here, all of these three constructors of the symbol class, they all use the offset field. Okay. So now each symbol has its own offset. Symbol table, I have also added a field called offset here because I need to know how many symbols there are in the symbol table and how much space we have allocated to local variables of the symbol table. So this is the offset which holds that how much space has been allocated to local variables. This is not like individual offset, this is like more of an aggregate offset for a particular function, let's say. Okay. So here we just initialize the symbol table with some offset, and now this offsets all must be 16 byte aligned, which is a mandatory requirement on x86. So whatever offset value is given into the constructor is aligned to 16 byte boundary. Any questions about this? So this is how you align anything to a 16 byte boundary. This is the way, like you just add it with 15 divided by 16 and then multiply by 16. So any questions so far? What is alignment? So alignment, suppose you want to align to a 16 byte boundary. That means that your addresses can only be in multiples of 16, like 0, 16, 32. It cannot be, your address cannot be at 8. Whatever variable or whatever stack frame cannot start from address 8, because 8 is not a multiple of 16. That's what 16 byte align means. Okay, why is the offset of the symbol table required? Can anybody answer this? Sorry. So actually it's not, actually the offset is probably a bad name. Basically it says that how much space is being allocated to the symbols. Like, so you want to know like how much total space to allocate. It's not just address alignment. So address alignment says where a particular address should start, right? But size is a different thing, like how big should be the area you need to allocate for local variables. No, right. So that's a good point. So the address, the area allocated to local variables must be aligned on a 16-byte boundary, but symbols themselves each occupy 8 bytes because it's a 64-bit architecture. So the size of the entire local variable area may not be a multiple of 16. It is a multiple of 8, basically. Okay.
Each symbol is multiple of 16 and in symbol table is stored as
No, each symbol occupies 8 bytes. Okay, so there's a difference. So there's a offset of the symbol. Okay, each symbol is stored at some offset from the top of the stack, right? Now, since each symbol in a 64-bit architecture occupies 64 bits, so so this symbol offset is basically always a 8 multiple of 8. It always has to be. Okay, so the size of the area allocated to local variables is a multiple of 8. However, the local variable area can start only aligned to 16-byte boundaries. It's different from the size. The start address is different from the size. Okay, does that make sense?
And how is this linked to the size of the symbol table? How is offset linked to the size of the symbol table?
So there's a so here by offset of symbol I mean where the particular variable is stored, and offset of the symbol table what I have tried to signify is what is the size of the area allocated to the
Offset be able to decide the size.
so yeah, it's probably a bad name. I probably shouldn't have called it offset. This symbol table offset probably should have been called something like area or something like that.
But it's not going to give an address or a particular boundary where the symbol table should start.
Yeah, so initially, so if you see this constructor, it has only one argument, which is the offset at which. So this OS says, what is the offset at which this stack frame must start? Okay. Sorry? Yeah, so let me just say stack frame for the function, let's say. Now, if typically people would give the offset as a 16-byte aligned thing, but if someone didn't give it, then you would have to align it explicitly to 16-byte. Okay. Okay, any other questions? Okay. Right, so now what are the new additions? So in this part where we are inserting symbols into the symbol table, so that we did for PD3 as well, but here every new entry into the symbol table is receiving an offset. Okay, so that's a additional information that we must store for every variable. And note I have used it as 8 because I'm using a 64-bit architecture. So every time I'm incrementing it by 8 bytes and assigning a offset. So every symbol occupies 8 bytes, basically. You can think of it like that.
we didn't do it in insert const.
Okay, so before I go to insert constant, let's take a look at this insert and this add. So insert basically inserts a variable, add inserts a temporary variable. Yes.
You're saying that each symbol occupies 8 bytes, so the symbol is a structure. And that structure.
Oh, okay. Okay. So symbol, what I mean by symbol right now is local variable. I mean, so there's this compiler symbol which we are using here in this PD3 and PD4, which are like entities of the symbol table which keep track of which data item we are referring to, right? But when we go into the world of actual execution, where we are actually executing assembly code, This symbol is not a structure anymore. There it's just a space, a set of 8 bytes. Whatever value resides there is the value of that variable. Whatever reading, writing is like reading, writing. It's just a set of 8 bytes. That's all it is in the world of execution. But in the compiler world, a symbol has a lot of things. It has a name, it has a address, it has some other attributes with it.
My doubt was, we have symbol string for every symbol, there is string name. That string can be arbitrarily long.
Yes.
That may have an effect on the size of the symbol.
Okay, so the question is that in the class symbol, we have this a string which is the name of the symbol, which can be arbitrarily long named. Does it have any impact on the amount of storage we need to allocate for that symbol? So no, we are not going to be referring to symbols by their name. In the assembly code, we're not going to be referring by their name, not going to be storing their name. It will just be an address by which we refer to them. Okay. Question?
That address is 64 bits long, therefore each symbol will require a scientific address.
No. So 64-bit architecture basically does everything in multiples of in 8-byte increments. So registers are 8 bytes long. The data items are mostly 8 bytes long. But does that imply it has a 64-bit address space? No. That's a different issue. Okay. Where? Here?
Yes.
Okay. So here basically the start of this whatever local variable area has to be 16-byte aligned. So this is a standard way to align anything to 16 bytes. If you want to align something to 8 bytes, you would have to write OS plus 7 whole divided by 8, then whole multiplied by 8. That's the standard way. Okay. Okay. So anyway, so we have allocated space to each variable and incremented the offset by 8 each time. Now this insert const, like you said, like that is not allocating any offset. So insert const is basically for symbols which are constants, which are not really variables. So we have variables, temporaries, and constants, right? So constants are like 5, 10, 12. These are constants, okay? So these constants we are storing in the symbol table just to keep things uniform. But we don't really need to allocate memory to hold a constant. We need to allocate memory to hold variables because variables have different values at different points of time. But constant is a constant, its value is known. We don't really need to allocate space and store the constant. So that's why we are not incrementing the offset when we are inserting constant. Even you can do that, it's not going to be wrong, but it will just allocate more space than is actually required. Yes. Right. So that's a good question. So if we are not storing the constant in memory, but we need to refer to the constant, how do we do it? So so I'll come to that in a little while, that how we deal with these constant symbols, okay? But right now, what I'm just saying is that you don't need to allocate memory for it. It's not necessary. If you think it makes your life simpler, go ahead and allocate it, but it's not going to serve any purpose, okay? Okay. Okay, so this is for insertion of the variables. Now in quadrilateral, the quad table class. So here not much has changed. However, in the in this quadruple class, we are converting 3 address code to the assembly code. So 3 address code, remember, it's the intermediate code, right? Now we need to convert it to assembly code. And since quadruples are a natural way to store the 3 address code, it's also natural to implement this conversion to assembly code in this quad class, right? Okay. So, so this particular print function was there before also. I mean, it was just being used for printing 3 address code. So that continues to remain. We may want to use this to debug and all. Then I have added this function print assembly. So basically what print assembly does, it prints the assembly code version of this quadruple. Okay. So here I have mostly just implemented 2 operators. One is the addition operator, one is the assignment operator. So if the operator is addition, I call the function print add. If the operator is assignment, I call the function print assign. So let's see what print add does. Basically, print add first generates source code, generates code to read the first source, generates code to read the second source, then actually prints the addition statement, then generates code to write the destination value, and then just leaves a blank line so that we can, like, it's easier to read. This is not mandatory leaving the blank line. I just kept it to make it easier to read. Print assign, which is for printing the assembly code version of assignment statements, just reads the first source, writes the destination, because there is no other function. There's no second source. There's no operation to perform, and that's it. Okay. Any questions? Okay, so what does this read sources and write destinations do? So these are routines that were called. So this read the first source, then this routine is read the second source, and this one is write the destination. Okay, so read the first source. Basically, to read the source, what we have said is, okay, here is the symbol ID, because we need to know what to read. And yeah, I actually need that, but anyway. So the first source is read in this way, that here we have this. So if you see this particular line, actually, can you read it? I probably forgot to increase the font today, but nobody complained. Okay, so here is the, here's where we are actually generating code to read the source. So here we just say move, basically just to transfer some data, something at an offset from this RBP register, which is our frame pointer, and move the data into the RAX register. So once this particular instruction will have been executed, the value of the first source will be there in RAX. Okay. Any questions so far? Sorry? Count. Okay. So count basically is saying, like, so if you remember, we had said in this one of these classes that for each 3 address instruction, multiple assembly code instructions will be generated. For example, if you have an addition, there will be one assembly instruction to read the first operand, second assembly second operand, then one add, and then the 4th instruction will write back. Okay. So now what labels should each of these get? So a good way is to, it makes life easier if you generate label for every statement, instead of trying to make a decision which statements may need labels, which statements may be jumped to. That makes life a lot more complicated. Easier way is to generate label for each step. Now we could reuse whatever level the original 3 address instruction had and could use this for the assembly code. However, since there are multiple state assembly instructions all corresponding to the same instruction, and we cannot give the same label to multiple assembly instructions, so we need to kind of augment the original 3 address label by another field which says like, okay, this is the label of the original 3 address instruction, then it is followed by what is the instruction ID of the assembly instruction for that particular 3 address instruction. So this is what count signifies, that whether it's the first assembly instruction corresponding to the 3 address instruction, the second or the third or whatever. Okay. Any other questions? So here what Rahul asked, this part is, how do you print out constants? Like if you're not going to be storing constants anywhere in the memory, how are you dealing with them? So constants basically can be addressed by just using the dollar sign. You don't really need to read them. You can just put the constant in some register, in this case RAX, and go from there. So let me just show you an example that will make it clear. Okay, so here was my test case. So here is a test case, very simple test case. Only one function, 2 variables, only assignment and addition. Okay. So what did we do? So the first one is z equals to 5. Okay. So let's see how we generated code for that. So right. So first one. So here is the symbol table. I printed out the symbol table for debugging purposes. So before for PD3, we only had the variable name and the data. The first 2 columns were there. Now I have added some extra columns. The third column is the offset. So Z has an offset of 0, W has an offset of 8 since it increases in 8. T0 has an offset of 16, T1, 24, and so on. 5 and 10, which are constants, basically, not variables, I've given them like garbage offsets because they don't really need space. I have also used another field, true and false. Can anybody say what the 4th field signifies? Whether it's a constant or not. Exactly. Okay, so here is a symbol table. Now, the first one, let's say we are generating code for this first one, L0, Z equals to 5. Okay. So this is the code for the first one. Okay. Just ignore the first 7 lines for the moment. Just look at this L01 and L02. Basically what happens here is we move the value 5 into the register RAX, and then we move register RAX to whatever is the location of RBP. Okay. So this is why we don't need to store the value of the constant anywhere on the stack or in the memory, because we can directly refer to constants in assembly code. We can just say $5 instead of having to store 5 somewhere, then reading that and so on. Now this code is also very inefficient because I don't really need to put 5 in RAX, then move RAX to that. I can directly move 5 there. But that will require more complex code, so I didn't do it. Okay. Okay. So does that answer your question, Rahul? Okay. Now there is another example. Let's take a look at this L2, where W is equals to Z. Okay. So sorry, yeah. So L1 W equals to 5 is there. So L1 is similar, very similar to the previous one. L2 W equals to Z is these 2 lines. So here basically Z is being read into RAX, and RAX is being transferred into the location of W. So, and why, how do I know that this is Z and this is W? So if you see in the symbol table, Z had a offset of 0, W had an offset of 8. So when I am taking the offset of 0 with respect to this RBP, which is the frame pointer, that means I'm accessing Z. And when I'm taking an offset of 8 with respect to the frame pointer, that means I'm accessing W. That's how I know that this is correct. Okay. Any questions about this? Yes. Why is it? Okay, so the question is, why are the offsets -8 and not +8 and right? So the reason is that in x86 the stack grows into lower addresses. So if you want to grow the stack, you have to decrease your address. That's a convention in x86. So basically, although I didn't store the offsets of the variables as negative numbers, these are actually negative offsets from the top of the stack, because the stack is growing into lower addresses. Okay, so that's why when I actually generate the code, I have to give the address as a negative. But I just store it in positive. I mean, it's the same thing actually. Yes. Why are we not using a stack pointer to? Okay, can anybody answer that? Anybody want to answer that? Why we are not? Why using the frame pointer instead of the stack pointer? Right. So basically, the frame pointer is static while the stack pointer is not. When you push and pop, stack pointer is changing. You don't know where it is. But for a particular function, frame pointer is going to remain at the same place. So, yes. Yes. Somebody had a question over there.
Yeah. How could you switch back to the code?
Yes.
Where the offsets would be generated.
Okay. Yeah, here it is. So here the offset is being, every time you encounter a new symbol, you are incrementing the offset by 8. That's it. Okay. So basically, read source 1 reads the first source, read source 2 reads the second source. Can anybody say why I need 2 different functions for reading source 1 and source 2? Why not do it with just the same function? Different registers, exactly. One of them puts in Rx, the other puts in RB. Okay, now the last one is you write your destination back. So what I'm doing is I will manipulate every operation, like for example in the case of this add operation, to make sure the result resides in RAX. So for example, when I write add RBX comma RAX, that means add RAX and RBX and put the result in RAX. So that's what the format essentially implies. So I am kind of assured that every time once I perform the operation, the result is in RAX. So the write destination function just basically takes whatever was the value of RAX and moves it to the correct offset with respect to the frame pointer. Yes.
In system.out.println, basically statements are getting printed.
Yes.
Where are the actual operations getting done? Using add, rex, and rbs is in double quotes. It is just going to print. But the original operation where it is going to be done is how it is executing the operations.
Okay. So the question is that, oh, we are printing out the assembly code, but how is this getting executed? That's a good question. So basically, yeah, just printing out the assembly code will not execute the program, right? So preferably we should print the assembly code out to a file. Okay, so let me do that. So let me so I'll just copy this, but you should just print it out to a file instead of doing this copy and all. So I put the assembly code that was generated in a test.s. The like .s signifies assembly code to the GCC compiler. Then I compile it using GCC. Okay. So if you see, GCC will has created an executable a.out. Now I execute a.out. So it didn't have any printf statement, so it didn't print anything, but it runs. So I can add some printf statements to check that it works or not. So sorry. LTR is a Linux command. It just lists the files in the directory with the timestamp and all, and the permissions. Okay, so let me just add some code for printing out just by hand, not programmatically. Okay, so I have added some code to this assembly file that I generated by hand to print out the value of z. You shouldn't be adding any code by hand, by the way. Everything should be programmatically generated. So I will compile it again and run it again. So here now we have some output, and let's see if the output was correct. So so z was initially 5. Then Z became 15 when we did the W plus 10, and then Z again became 10 at the end. So, and that's what we get when I print it out, that Z is 10 basically. So printf usually gives you the idea that you have your program run correctly and all that. Okay. Okay, so here we have all this, we printed everything. This particular function prints the label. So I think your real task here will be to write the print functions for all the different operators. So I just did it for 2 operators. You have to write it for all the other operators that are there. Okay, now for the quadruple table, so this was the functions we had in just the quadruple class. For the quadruple table, I have this function print assembly, which first prints a header. Then for each of its quadruple, it calls the print assembly function, and then it prints a footer. So what are header and footer? So this print header is this function which is here, this part. So this part says that, oh, the main is a global symbol. So it's there's a function main, that symbol has global scope. Dot text says now the code is starting. Then yeah, I think this is a mistake, but main should appear. The label main is there to signify the beginning of the main function. And these first 3 lines, they basically make space for the local variables. So first line here saves the original frame pointer. Second line here makes space. Second line here sets the new frame pointer, and third line here makes space for the local variable. So these are 3 lines you have to write whenever you enter any function, right? And everything will be the same except this, the amount of space you leave for local variables. That's going to be different for each function. Okay.
How will we know how much space?
Right. So the question is, how will we know how much space to leave for the local variables of each function? So that information should be given by your symbol table. Your symbol table should know how many local variables this particular function is using, and that will be the value. So if you see in this code, the SymTab class had offset as one of the fields. That kind of stores what is the amount of space I need to allocate to accommodate all the local variables for this. This is what? Yeah, constants I haven't stored. If you feel like, you can store it. Because we are not going to be checking the assembly code that is generated. You'll just check the output. Run the assembly code and check the output. Okay. Okay. So where was I? Which other extensions? Okay, so the question is, does the assembly code file have to have the .s extension? Can it have extensions like ASM? It can. The only thing is GCC directly compiles .s files. We don't have to do anything. And I'm not sure that the case is the same with ASM. Yeah, so I mean, since we want to keep a uniform way of testing the code, so just following this. Also, ASM, some of the formats may be different. Like this exact format of the assembly code, whatever symbols, percentage, and dollars we have used, would probably not work directly in ASM. Yes?
And this is the AT&T syntax. This is not the ASM syntax.
Exactly.
This is Indian syntax, ASM. And the header is also different.
Exactly. So if you do it in ASM, first of all, it will be another a different way we have to test the code, and you also have to you probably won't be able to borrow this demo code directly. You will have to write it yourself, right? Okay, so
How does it know that what kind of machine assembly code it should generate so that it executes?
okay, so the question is that when we install a compiler, how does the compiler know which machine's assembly code should it generate, right? Okay, that's a good question. So whenever you are installing something like a compiler, you have to configure it. You can't, there is no vanilla installation for compilers. You have to configure it. You have to give it some parameters like what machine is this. So by the time it is installed, it knows what machine it is on, and that's it. So one way compilers can do it is they can pick up this information from the OS. What is the machine they are on? But there is also another thing called a cross compiler. So cross compiler basically it may be something, an example of a cross compiler would be the compiler is installed on an Intel machine, but it generates assembly code for ARM. So a cross compiler cannot pick up this information from the OS because the OS doesn't know what it is supposed to be compiling. So in that case, the user who is installing it has to give it the information that although you are on an Intel machine, you need to be compiling for ARM. Okay. Did anybody have a question here? Okay. Okay, any other questions? All right, so so that was the header part, and here is the footer part that you must put when exiting from functions. Basically, this is the opposite of the work that is done in the header. Here, whatever space we had allocated for the local variables was by subtraction, if you see here. And here we add back exactly that amount of space so that the stack pointer goes back to the original space. And then we kind of, we had just pushed the frame pointer before this. We pop the frame pointer at the end to get back the older value. And then we just say return. Yes.
Question regarding the assembly code. Suppose we have a function defined in our file. So how does that respond to the assembly code?
Suppose we have a function.
Yeah. So let's say I have a function in my source code that prints something or that adds something. So how does that map to the assembly code?
Okay, so how do functions appear in assembly code? So functions, assembly code doesn't have the concept of functions. Function is a high level language concept. Okay. The functions mainly appear as this label here. It's like any other instruction label. Like if you have a function called foo, you would have just foo colon and then the function starts. Okay. There is no concept of function, but there is a concept of call and return. Okay. So call and return is more like a jump, like it can jump to any place. If you wrote assembly code. So what happens in high level language code? You can only call functions in high level language. You cannot call a random line of code, right? But in assembly code, you can call any address that's allowed because there is no concept of function. But there is the call and return concept. So it's a little different from the high level language world. Does that make sense to you?
Okay, so if I have a function, should it always be at the end of the assembly code file? Because if there is no concept of a function, so
No, it doesn't have to be that. Then what if you have many functions? How many will you? Function, there is no concept of function, but the function is demarcated by a label. Like the function main has been demarcated by a label. Now this label is no different from the labels for the for this L001 label. It's same in category. You can say call main. So also can you say call L001? You cannot do that in high level code. You can only call functions in high level code. But in assembly code, you can call any address if you like. Does that make sense?
Okay, so if we are making call, will it clear the registers A, B, and C, or all the registers?
If you are making a call, will that clear the registers? No, typically no.
It won't change any
No, but there is something called a calling convention, where there is an agreement between the caller and the callee that these are the registers caller has to save, these are the registers callee has to save, and so on. So we'll come to that. We haven't come to that yet. Yeah, you had a question.
The three lines following the second main label.
Yes.
What are they doing exactly there?
So they first save the original, the caller frame pointer value, then move the current value of the stack pointer to the frame pointer. So that is now the new frame pointer value. Yeah. So whenever you are entering function, you are doing this. And then you you have this space being allocated for the local variable.
And how is this being handled in the code?
In the
Generated in the code. These three methods.
Oh, how is this being generated in the from the compiler? Okay, so here in the quadruple table class, we have this print assembly function, which basically first prints the header, which is print header basically generates the top part. Then for each of those quadruples, it prints the assembly form. Then it prints footer, which is the bottom part. So I have used just one function, so it's a little bit easier for me. But,
We have always assumed that there is got to be at least one function.
yeah. So so this particular grammar that you are using in your class, no code can exist outside of functions. All the code is encapsulated within functions.
Last program, there has to be one function.
Yeah, there can be some variable declarations outside of functions, but no code. Yeah.
But in case I have a variable declaration outside of field, just before entry, if I declare a variable, then the header will print two main variables before the variable declaration.
No, you should print just one main level. That's a mistake. Sorry. Yeah. What is it?
Yes, that was my question. So if I have say int a10 or my int main, then according to print header, it will print out two main tables before actually processing that int
No.
a10 from the import table.
So no. So this first of all, there should be just one main label, and this main label is for the function. But before this part, if you have any global variables, so if you have local variables, they are not explicitly declared in the assembly code. They just appear as a space in the stack. But if you had any global variables, they are actually addressed by name. They are the only things addressed by name in this function, in the assembly code. So you would have to add them as, so I let me just show you. Sorry? Yeah, so I it was on the slide, basically. So here, if you have a global variable using this field declaration, that's the form that you need to put in assembly code. So there should be a dot data section under which this global variables will appear. So this is like variable I, then dot quad says this is quad word, basically a 64-bit variable, and 0 is the initial value of that. Okay. Okay, so so basically this is about it. There's not much more to show, so I don't want to like give you a lot more information and have it backfire. So I think I'll stop here today, unless stop here with the demo today, and unless you have other questions. Yes.
While in the print assembly function, you had print header and then follow for every entry quad table you are printing the assembly code. So the global declarations also have quad entries.
Okay, so the question is, do the global variable declarations, do they also appear as entries in the quadruple table? Because you're supposed to be generating code for them, right? That's your question? Okay, anybody want to answer that? It won't be a part of the quad table, so how will you handle it? So you need to generate some code for it, but I get the point that it's easier if it's part of the quad table, but see, so the good thing about global variables is that all of them will appear in the bottommost symbol table of the symbol table stack. Okay, they cannot appear in any other symbol table in the stack ever. That's the only place they can appear. Okay, so so since you know where they appear, it makes life easier. You don't really need to put them in the quadruple table. You can just go over the global symbol table and print that kind of the kind of code I just showed you for all the symbols in the bottommost symbol table. That's it. You don't need to put it in the quadruple table. That's the one symbol table that will be processed differently. All other symbol tables will be processed like I showed you, because all of them, everything else is a local variable. Okay. Okay, any other questions? Okay, so we'll stop here with the demo and we'll do a little bit of the lecture before wrapping up. Yes.
Just one example of a function called.
One example of a function call. So you know what, function call, I think finish the PD3, we'll do that next week. It's a little more involved, function call. Okay.